Okay, so we're on page 449 of the Math 20 um, workbook, absolute value workbook, and today we are looking at absolute value functions. So before we get into absolute value functions, let's take a look at just what absolute value means. So if we're taking the absolute value of a number, this definition that they've provided is a little confusing, but let's just go through it anyways. The absolute value of a real number is defined as the principal square root of the square of the number. So, for example, absolute value of 6, so we're going to square 6 and then take the square root of that. So the principal square root is, remember, always the positive. So we're taking the square root of 36, which is positive 6. The absolute value of negative 6, well, let's square negative 6, and negative 6 times negative 6 is, of course, also positive 36, and the principal square root of that is positive 6. If we're taking the absolute value of something, we use absolute value bars. So you can see the absolute value of A is written as A with the little bars around it. Okay, so if we take a look at this little policeman here, our math cop, says, to me, this is probably a little bit easier to understand. So the absolute value of a real number is the distance of the number from 0 on a number line. So how far is negative 6 away from 0? It's 6 units away. How far is the number 6 away from 0? It's also 6 units. So the absolute value of 6 and negative 6, both of them is 6. So it's almost like me asking you, well, how far did you drive to get to school? Or how far did you walk to get to school? We're not worried about direction at all. It's just basically how far did you come. So the other thing that he notes is the absolute value of a number will never be negative. And so the only thing that I caution you on that is a lot of times people say, oh, so you mean anytime I see any of these questions, so all of class example number 1, it's never going to be negative? That would be false. What he's saying is essentially anytime I've got absolute value, and regardless of what you have, if you have an operation, anything within the absolute value bars, yes, that will never be negative. It will always be positive. So if you have other things going on outside, so for example, if we looked at C or D or G, then it's possible that it could actually be negative. Okay, so let's take a look then. Class example number 1A, absolute value of 3. So how far is the number 3 away from 0 on the number line? Of course, it's just 3 units away. Same thing, how far is negative 3 away from 0? Is 3 units. So in this case, the absolute value bar, you have to think about them almost as an operator as well. So kind of like brackets, but also an operator. So it's saying how far away from 8 is it? 8 units. So then this is negative 1 times the positive 8 units, which is then negative 8. In this case then, the absolute value of negative 8 is 8, but then it's the negative of that. So the answer here is also negative 8. We cannot, as we would with brackets, say, hey, it's negative 1 times negative 8. That does not work like that. You have to apply the absolute value bars first. If we take a look at part E then, so we've got 2 separate pieces here. The absolute value of negative 7 is, of course, 7, plus the absolute value of 7, which is also 7, and then that is 14, our sum. For F, this is where it kind of acts like brackets, so then absolute value of whatever 1 minus 5 is, and that is absolute value of negative 4, which is then 4. And for G, we're looking at, it's almost like negative 1 times the absolute value of negative 1 times the square root of 81. So Square root of 81 is 9, but then there's a negative in front, so then we've got a negative 1 times the absolute value of negative 9, which is negative 1 times 9, or negative 9. Awesome. Okay, so now that we've done a little bit with numbers, let's take a look at absolute value with functions. So we'll start with a linear function. So let's look at the left side here. So number one, considering the functions g of x is equal to x and h of x is equal to negative x, whose graphs respectively, the equation, so remember g of x is just kind of like saying y equals. So it's like having y equals x, and also for h of x equal to negative x, so y equals negative x. So in terms of graphing, we know slope is 1, y-intercept is, of course, 0. So let's use my line tool, and so y equals x should look just like so. So this is y equals x, and then y equals negative x then is going to be a negative slope. So we're looking at this. I'll just label that y equals negative x. And so we've sketched and labeled, perfect. So let's take a look at the second one. So consider the function f of x is equal to absolute value of x, which has the same equation of y equals the absolute value of x. So complete the table of values. So if y is always the absolute value of x, so y is equal to the absolute value of negative 5, which is 5, absolute value of negative 4, which is 4, and so on. So just hit pause and complete that table of values, and then go ahead and plot the points and join the points, and come back and hit play when you've done so. Okay, so it should look something like that. So this is, of course, y is equal to the absolute value of x then, when we plotted those points on. So explain the similarities and differences between the graphs on the two grids. So what can we see that they have in common? Of course, is when y, oops, so what we see then is they're identical in quadrants 1 and 2. And so what is happening there is when y is greater than or equal to 0, so in quadrants 1 and 2, the graphs are the same. Okay, or I guess the same, or we can say it's obviously it's a combination of the two graphs in of y equals negative x and y equals x. When y is less than 0, then the graph on the right, so the graph of y equals absolute value of x, has no points. Okay. So what we see, though, is that the graph on the right essentially is comprised of two straight lines. It's comprised of part of y equals x and part of y equals negative x. And so the equation of the line in quadrant 1 is y equals x, and in quadrant 2 it's y equals negative x. So how do we then indicate that it's those two parts? Is we call it two pieces actually, and it's each got a different domain, and so that's where we call it a piecewise function. So f of x looks like, we would say, so y equals x when x is greater than or equal to 0, and y equals negative x when x is less than 0, and so that's our piecewise function. And so a lot of times people do ask, well, why is it greater than or equal to 0 and not less than 0? Why isn't it also less than or equal to 0? And obviously, yeah, it also looks like a negative x when x equals 0. However, we don't want to have the equal to 0, that value for 0 for both of them, so it just belongs to one or the other. So typically speaking, we assign it to the positive graph is usually it. You could assign it to the negative graph and not the positive. That would be fine as well. Okay, so let's take a look then. So it says defining the absolute value function. And this is a little bit confusing, but it's still worth going through. So f of x is equal to the absolute value of x, and remembering that it is the principal square root of the square of that function. And then it equals x when x is greater than or equal to 0, negative x if x is less than 0. Okay, so let's take a look at this particular function. So the absolute value of x minus 3. So once again, they're calling g of x x minus 3, and then h of x the negative of x minus 3, also known as negative x plus 3 if you distribute the negative. Okay, so go ahead and complete. You can see these two table of values right here, and they've just written them horizontally instead of vertically, as some of you might be used to. And then go ahead, plot those points in the grid, join the points, extend the graphs, and then go ahead and do so for the absolute value and take a look at what happens. So go ahead and hit pause right now and then rejoin me when you're done. Okay, so hopefully what we notice is just exactly the same as what we had on the previous page, and that is that when y is greater than 0, greater than or equal to 0, the graphs look the same in quadrants 1 and 2. And same thing for the absolute value graph. Again, there are no points in quadrants 3 and 4. So that should give you a little bit of a clue then, hopefully, as to how to actually go ahead and to draw it. As well, we're also needing to work on our piecewise function and writing that out. So what are we noticing is that this line to the right sure looks a whole lot like x minus 3. And so if this part of the graph on the right here is x minus 3, when does it look like x minus 3? It sure looks like it when the domain values, the x's, are anything greater than or equal to 3. And when does it look like the graph of negative of x minus 3 or negative x plus 3 is when the domain is comprised of values that are less than 3. So notice, why is that relevance of that 3? Again, that is our x-intercept, and so that's going to come into play as well. So if we go ahead then and write our piecewise function, you can see they've divided this up into f of x, so y is equal to x minus 3. So it's essentially saying, hey, the graph of the absolute value of x minus 3, so the graph of f of x sure looks like x minus 3, this red portion, if x is greater than or equal to 3. So it includes the equals because we're looking at the positive portion of it. So when inside the absolute values is positive, so that's to the right here. And it looks like the negative side when x is then less than 3, and 3 being the x-intercept as well. Okay, so let's carry on then. So explain how the equation of the second piece can be determined from the equation of the first piece. So the second piece, the equation is simply the second piece is the negative of the first piece. Okay, so we can basically take the first piece and multiply it by -1. So for example, -1 times x minus 3, or you could also write -x plus 3. You could also write 3 minus x. They're all going to be the same thing, and any of those three expressions could be written as the second piece. Okay, so explain algebraically without using the graph how the domain for each piece could be determined. So at the end of the day, we want to find the 0 or the x-intercept. Okay, so obviously x-intercept when you're graphing, 0 if you're not using the graph. Okay, so we would know that that 0, that x-intercept, divides the function into two pieces, and so call it, so the 0 or the x-intercept called, let's just call it P. So we've got two pieces. So we've got when x is greater than or equal to P, and we've also got when x is less than P. Okay, so some key points then. Every absolute value function can be defined in pieces. So that is our piecewise function. And that is essentially a description of the graph then and its two pieces. The absolute value of a quantity will always be the same quantity if the quantity is positive, and the opposite quantity if the quantity is negative. It's a lot of quantities. Writing an absolute value function in piecewise form is important, an integral part of determining the solution to equations and inequalities, and we'll get to that shortly. Okay, so expressing this as a piecewise function, so we've got a couple of different ways of going through it. First thing that we could do is just to go ahead and find the zeros of that. The other way to go through it is to actually work through the zeros as you're writing out your piecewise functions. So let's go through that part first. So if we were to say f of x is equal to, and you're going to practice your fancy step brackets, so we've got the positive version of 3x plus 2. We also have the negative of that, so the -1 times 3x plus 2, or if you wanted to write -3x minus 2, that's fine. And so when will it look like 3x plus 2? It will look like it when 3x plus 2 is greater than or equal to 0. It will look like the negative version when 3x plus 2 is less than 0. And so then we're just going to rewrite it again, cleaning that up. So again, it looks like 3x plus 2. We clean this up, so subtract 2, divide by 3, so x is greater than or equal to -2/3. And then same thing here, we can leave it as negative times 3x plus 2, or if you want, -3x minus 2, and that occurs again when x is less than -2/3. Okay, this one's a little bit trickier perhaps, and it will certainly come up when we're solving our absolute value equations. So when we've got the absolute value of form minus x in piecewise form, so we could say g of x, instead of that, well, we used f of x before, so we'll call this one g of x is equal to, well, it's the positive version for minus x, when for minus x is greater than or equal to 0, and it's the negative of 4 minus x when 4 minus x is less than 0. So again, clean that up, and so then we've got 4 minus x when an isolating x in this case, so we could just simply add x to both sides, so 4 is greater than or equal to x, which means that x is less than or equal to 4. And then here, if we distribute the negative in, we could have -4 plus x, or you could also say x minus 4, or you could just leave it as is. That's okay as well. And then again, adding x, so then x is greater than 4. So this one's tricky because a lot of times people always assume that for the positive version that it's always when x is greater than or equal to. But the thing is right here, one of the things that you can recognize as well is if you were to graph 4 minus x, that is what's going to be going up to the left because it's got a negative slope right here, and then on the other side we've got the positive slope. And so if you thought about it, then if I just looked at where my x-axis is, this point right here, my 0 or my x-intercept, that is at 4. So it looks like 4 minus x, negative slope, when x is less than or equal to 4. It looks like the positive slope, which is actually the negative of my original function, when x is greater than 4, or it's to the right of 4. Okay, thank you, and let me know if you guys have questions.